Welcome back. So we are starting our second module and we want to talk about deep learning training techniques and heuristic. So to understand these methods, it is essential to talk about deep learning architectures. So the reason we want to do this is because the training problems that we're going to deal with, the optimization problems, are very difficult problems, right? So to tackle them, we need to identify structures and leverage those structures to find effective and efficient solutions. And one way to understand those structures is to actually understand the architectures of the deep learning models we want to optimize in the first place. So my hope is to be able to drive these architectures as solutions to the simple models that we are familiar with, such as linear regression, as opposed to just tell you what these architectures are, okay? Therefore, we're just gonna go back again to the simple model we have seen before, linear regression, and we wanna see how we can think of that as a simple deep learning architecture and how we can build upon it to basically come up with more complex deep learning architectures to alleviate the issues of this linear regression approach. Okay, so recall for a simple linear regression model, we are basically assuming that the relation between the features and labels is given by a linear relation. Okay, so again, let's assume that yi's are y labels, the features are xi's. So I'm going to assume that there is this linear relation, right? So where the regression weights are w star, and there's also some bias b star. Okay, so my goal is to learn this from data. So previously, when we talked about linear regression, we didn't talk about this bias term or the intercept term, and that's without loss of generality. And the reason for that is that whatever dimension your original problem, you can increase the dimension by 1 and define new w star and new features such as this. So you can augment w star and b star into just one parameter called the w star, and then add just this one as one of your features. Okay. So therefore, many times people ignore the bias term, especially when they want to talk about linear regression from a mathematical perspective. Okay. So what's the goal? The goal, again, as demonstrated in this figure, is to learn the slope and the intercept of a line that crosses through the data, that fits the data as well as possible. Okay. So that's the linear regression model. Okay, so we can think of this model as a combination of artificial neurons. Okay, so essentially neurons are elements that take an input signal, they process it, and then they pass it forward. Okay, so linear regression is nothing basically but as a very simple artificial neural network or a shallow deep learning, where we are taking these inputs, the input features, and then we are processing it. So for instance, we multiply it by the first component of w. So we multiply x1 with the first component of w. We multiply the second component with the second component of w, and so on and so forth. And we multiply the last component with the last component of w to get the output. Okay. So therefore, in the language of deep learning, this is nothing but a simple neural network with one input layer and one output layer, such that all that happens to the input signal, the features, is that we are just multiplying that by some weights and then report the result as our output. Okay. Now, what's the training problem? The training, again, involves fitting the data. Okay. So we want to optimize over the parameters of these neurons, essentially the weights and the biases, which are our regression parameters. So we want to optimize them such that we have the best fit to the data. So it is also very useful to think of linear regression as a maximum likelihood estimation problem. Okay? So essentially, we assume that we have some observations that are noisy, such that the noise distribution is given as a Gaussian distribution. Okay? and that the observations are statistically independent. Now, when we have these observations, and a useful principle in estimation theory is to find the parameters such that the likelihood of the data is maximized. So the likelihood is essentially the probability of the observations given the features. So we want this probability to be maximized, therefore we want the likelihood to be maximized. Now, given that the observations are statistically independent, the likelihood over the entire training data is nothing but the product of these marginals. And if you're assuming that the observations are corrupted by independent Gaussian noise, that means that the distribution of each observation is going to follow a Gaussian distribution. So ignoring some constant, the likelihood is basically the product of a bunch of exponential functions, as I've written here. Okay? And our goal is, again, to maximize the likelihood. That means that we want to find the parameters of this distribution, W and B, such that the likelihood is maximized. And sigma here, you can just treat it as a constant which denotes the noise power. Okay, so for instance, it can be equal to 1. Now, we want to turn this into a minimization problem. And a useful trick is to leverage the log function. Notably, log is a monotone function. So that means that the solution to this problem is exactly the solution to another problem where I just take the log of the objective function. So we can use this idea, therefore, to take the negative log and therefore form the following negative log likelihood problem. So therefore, if you take the log of this equation here, multiply by negative sign, and ignoring the constant, you're going to arrive to this problem. Okay? So what is this problem? This is exactly an empirical risk minimization problem where our model is linear, and we are using the square laws to basically find the best fit to the data. So therefore, this maximum likelihood estimation problem is very nicely linked to empirical risk minimization problem for a linear regression model if we assume that we are dealing with a Gaussian noise. Okay? Now, this is very useful because we're going to extend this idea to a lot of more complicated learning tasks. In particular, most advanced learning tasks follow a similar template. They hope to maximize the likelihood, right? But given that the situation could be a little bit more complicated, they may assume different distributional assumptions. So here we assume that the data is IID and the noise is Gaussian. Depending on your learning task, we may replace these assumptions with something else. Okay. And it is also useful to talk about the concept of prior or regularization here. So using this idea, we can assume that we know some prior information about the input. Okay? And we can use that prior information as regularization. For instance, a useful and very frequent regularization term added to this kind of objective is L2 regularization, okay, where we just add the Euclidean norm square of the parameters with some regularization constant lambda to the objective. Okay, so we're going to include the regularization term, and this is something we're going to talk a little bit more in one of our future lectures. Now, after adding this regularization term or this prior information on our unknowns, the problem basically now is called maximum a priori estimation, or MAP, as opposed to maximum likelihood estimation. All right. So there you go. So when we are talking about a simple regression problem, perhaps the most simple model is a linear regression model. And we talked about the connection of that to deep learning. And we mentioned that we can think of it as a very simple neural network. such that the training involves minimizing the square loss over, or the average square loss over the entire training data. And we also talked about this very nice connection to maximum likelihood estimation. Now, what we want to do next is to extend this idea from regression to classification. Okay. So in particular, instead of assuming that the labels are scalar and belong to R, we have a classification problem with capital C classes. Okay. So for instance, a famous data set is the MNIST data set, or another famous data set is C for 10. And in both of these data sets, we have a classification problem with 10 classes. So C is equal to 10. Okay. But C could be even larger for a lot of other data sets that are very frequently used in the literature to test the capability of deep learning models and deep learning training algorithms. Okay, now for these kind of problems, it is a very useful idea to find a good representation for the labels. Notably, it is very frequent to use what we call one-hot encoding to represent these categorical labels. Okay, in particular, we're going to encode each label to a vector in RC. So in particular, yi is going to be one of the following vectors, E1 through EC. So what are these vectors? These are basically the standard unit basis vectors in RC, such that EI is all 0, except it has a 1 at the IS position. Okay, so this is called one-hot encoding. Now, after this encoding, we want to find a model to classify the data. Again, we're going to go back to the most simple model one could imagine, and that's a linear model. Okay, so we're going to assume that the relationship between the labels and the features is going to follow a linear model again. Okay, so in particular, we're going to have a relation like this. Note that previously, in the case of regression, W was a vector. Here, W, which I'm using the capital W, is going to be a matrix. And the reason for that is that now, after this encoding, our output is not a scalar anymore. It's actually a vector in RC. Okay, so if you have 10 classes, the output is a 10-dimensional vector. If you have 2 classes, the output is a 2-dimensional vector, and so on and so forth. Okay, so these are our labels and features. And what are the learner parameters of this linear model? Are this weight matrix and the bias. Now, again, we can think of these as an artificial neural network, basically a combination of neurons that take an input signal, process it, and pass it forward. In this case, again, we have a single input layer and a single output layer. Now, as I mentioned, given that the output is going to be a vector, we take the first feature, we multiply, let's say, with W1 1 to get the first output, and then there's going to be a link from this to all the other outputs as well. For instance, W1 2 and then W1 3, and so on and so forth. Okay. Now, what are these outputs? The outputs are basically the labels, right? But it is very useful to think of them as the probability that a specific, let's say, image belongs to a specific class. For instance, we can think of yi as the probability. So let me write it here. Yi as the probability that, let's say, image X belongs to class I. Okay. Now, this is very useful and important, as we're going to talk about in a minute. Okay. Now, let's talk about training. So we have our model. Now you can think of training. And we talk about how we can train a linear regression model. And we arrived at a square loss. Okay. And the path we took was from the perspective of maximum likelihood estimation. So you could think of that we can again use the square loss as before to find these weights, right? So the classification, the weights of this classifier, okay? And we can indeed do that, and it will work in practice. But it turns out it's not an elegant solution. Okay, and the reason for that is going to go back to what I mentioned earlier, that we should think of the output as the probability that a specific image belongs to that class. Okay, and it turns out that if we use a square loss, we're not going to necessarily have this nice structure. Okay, so for instance, let's imagine that we use a square loss or something like that to learn the parameters of our model. Let's call them W hat and WB, and then we have this linear relation. Okay, so as I mentioned, it is very desirable to think of the CS entry of the output as the probability that the label of this input X is C. Okay, for instance, this is an image of a dog. So if class 1 is the class of all cats, class 2 is dogs. So I want the first entry of Y hat to denote the probability that the image belongs to the first class, meaning the class of all cats. So it should be a very small number, near 0, if I have an image of a dog. And otherwise, the probability is going to be large if I have an image of a cat. Okay, but we're not going to get this necessarily if we through this linear relation. Okay, so if I use this in conjunction with the square loss, it's not necessarily the case that the entries, I can think of the entries of these as probabilities. Okay, so we want to ensure that this is like a probability. Okay, so what are the characteristics of a probability vector? So each coordinate should be non-negative, and all coordinates should sum to 1. In particular, the vector should belong to the simplex. Okay, so we want non-negativity and the fact that the entries sum to 1. And we're not going to necessarily have that if we just use this linear model and train it with a square loss. Okay, it turns out that we need some sort of normalization. Okay, so we basically want to normalize this Y such that entries are non-negative and they sum to 1. Okay, that's basically normalization. And one very useful way to do this normalization is called softmax normalization. Okay, where we basically use the fact that the exponential function is always positive and a simple normalization to ensure that the output is actually like a probability. Okay, so what's softmax normalization? So let's consider the outcome of our linear model. Now, instead of reporting this as my output Y, I'm going to apply a softmax operator on that. What's the softmax operator? It's best to define it entry-wise. So the JS entry of this softmax is basically you take the exponential of the JS entry of O, and then you normalize all of these exponentials by including this normalization term in the denominator. Optionally, you can have a parameter kappa here, which is called the temperature. Now, the motivation for this softmax operator actually goes back to physics, and in particular, the Boltzmann distribution in physics, which is a very famous model to characterize distributions over energy states in gas molecules. Okay. In particular, here, for our case, we can think of our finite classes, 1, 2, 3, up to capital C classes, as a collection of finite states. Okay, so therefore this distribution gives it talks about what's the chance of an input, let's say an input image, belonging to a specific state. All right, so that's basically our very simple classification model. We're going to use a linear model like before, but because we want this nice feature that the outputs represent the probability that the input belongs to a specific class, we also leverage softmax normalization. So what's the training process then? Then the training involves finding parameters such that we get the best fit to the data. Okay. So we need to come up with an optimization problem. In particular, we need to come up with a loss function. So for regression, we had the square loss. And if you recall from our lecture on basics of machine learning, we talked about classification and logistic regression in particular. And we mentioned that the loss that we use in those cases is actually the cross entropy loss. Okay. Now that doesn't come out of blue. So we're going to see that we can actually derive that cross entropy is a very natural loss to use for classification problems by following the principle of maximum likelihood estimation. Okay? So we're going to resort to MLE, and we want to find the parameters that maximize the likelihood of data. Now note that we assume that we are using this softmax normalization. Therefore, a natural observation / noise distribution is basically the multinomial distribution. And this is nothing but, as we talked about in the previous lecture, a discrete version of the Boltzmann distribution. Okay. Now let's see how we can arrive at cross entropy. So we want to maximize the likelihood. This is essentially our likelihood. So the probability that the class or our state is J, given that the input features is X. Okay. And as we mentioned, after following the softmax normalization, here's going to be the output. Okay. Now we mentioned before that maximizing the likelihood is equivalent to minimizing the negative log likelihood, given that log is a monotone function. So here, what I'm doing, I'm just taking the negative log from this side. Okay. Now notice that our true labels after 100 encodings are basically one of the standard basis vectors, meaning that all entries are 0 except 1. I can use this quantity here to include this summation here. So in particular, I'm going to go from this side to a minus sum over all classes yj times log of y hat. Okay, and as I mentioned, only one entry of y is 0. So only one entry of y is 0. Therefore, I can include this sum and still get an equality. Okay. Now this is exactly the cross entropy between y and y hat. So in particular, what I'm doing here, I'm viewing y and y hat as two probability vectors. Okay, and cross entropy is basically a notion of distance between these two probability vectors, between these two distributions. And as we're going to talk about in the next slide, it is also very related to a notion of distance from information theory called Kullback-Leibler divergence, or the KL divergence. Okay, so let's talk about a little bit. Let's talk a little bit about the connection between the KL divergence and the cross entropy loss, to see why minimizing the cross entropy is essentially equivalent to minimizing the distance between the predictions and the true labels that we get from our training data. Okay. To do that, we need some concepts from information theory that you may have seen in other places. One concept we need is the notion of entropy. So entropy is basically a way to talk about how random a certain quantity is, right? Essentially, if a quantity is more random, we need more bits to, it has more information, therefore we need more bits to represent it, okay? And entropy is exactly characterizing the number of bits needed to represent a certain quantity. Okay, this is the definition of entropy given here. So I have a vector, a probability vector of dimension c. I can calculate this entropy by following this expression, and it turns out that entropy is always positive. So the more random this variable, the higher entropy, and the more deterministic it is, the smaller the entropy, right? Such that when P is basically 1 and 0 elsewhere, entropy is exactly equal to 0. All right. Now, from this entropy, we can talk about relative entropy, or KL divergence. So this essentially is saying how random one variable is relative to another variable. So in particular, the KL is defined by this expression. Again, you can show that it is non-negative. So, and it basically describes the difference between two distributions. It is useful to think of it as a notion of distance. Although this is not a distance because it doesn't satisfy, it is not symmetric. Okay. All right. So as a side note, KL divergence is actually an instance of a larger family of notions of distance in information theory, which are called F divergences. In particular, for any convex function, you can define F divergence with this expression. For the case of KL, our convex function is actually T log T. So if I change this function to something else, I may get a different notion of distance or divergence. For instance, total variation distance. Okay. Now, by looking at the expression for the entropy and the KL divergence, it's actually, and also reminding ourselves of the definition of the cross entropy loss, it's actually very simple to show this relation, that the cross entropy is the entropy of Y plus the KL divergence between Y, the labels we get from the training data, and Y hat, the predictions. Okay. Now, we said that we want to minimize the cross entropy if we want to follow the maximum likelihood estimation principle. Okay. Now, Y is actually fixed. There is no parameter here. It's a fixed quantity I'm getting from the data. So therefore, the entropy of Y is also fixed. So when I'm minimizing the cross entropy loss, that's equivalent to ignore this term completely. So therefore, minimizing the cross entropy loss is exactly equivalent to minimizing the KL divergence. Okay. So therefore, what are we doing here? By fitting the data, we are minimizing the distance between the probability of the labels according to the training data, which is Y, and the probability of the labels are predictions that we get as part of the training process. Now, as I mentioned earlier, you can actually use a square loss for classification, but it is not natural or elegant because it doesn't correspond to the maximum likelihood estimation solution. Okay. It turns out that cross entropy provides also larger feedback sooner. Okay. So essentially, there is another reason why we may want to use cross entropy when learning classifiers. So here in this plot, what I'm showing the loss value versus how good our prediction is. Okay. So early on in the training, we should expect that our model is not going to be perform very well. Okay. So the prediction therefore is not going to be very good. Okay. So in this case, if we were to follow the square loss, so this is the square loss, the loss value is not going to be terribly large. So as we're going to talk about, that the implication is that we're not going to get a very large feedback or signal that we can use in our, let's say, SGD algorithm to update the weights. So therefore, the training is going to be slow. Okay. On the other hand, for cross entropy loss, early on, when the distance between Y and Y hat is large, the loss value is going to be very, very large. In particular, it could actually be unbounded. Okay, so this means that we're going to get like a very large signal, very large gradient. Therefore, make a progress, a lot more progress early on in the training. And obviously, as our predictions are getting better and better, we expect both of these loss values to go to zero. So when the training is done and we have a very good model that can make great predictions, both of these loss values are going to be very, very small. All right. So let's talk a little bit about what I mean by the signal. So signal for us is actually gradient, because we are using iterative training algorithms such as SGD to update the parameters of the model. And to do that, we need to find the gradient. So the more informative the gradient, the better our updates are going to be, and the faster we can find a good predictor. Okay. So let's talk about this and the connection between the gradient and basically how good our predictions are, such that when we are making a mistake, we have a large gradient, therefore we can have faster training. To do that, let's consider our linear regression. Okay, first. As I mentioned, for training, we use SGD to minimize, let's say, the empirical risk minimization problem. Okay. Now, we need basically the gradient of the loss with respect to parameter to update the parameter. Okay. So, in particular, this quantity. So, for linear regression, it's actually very simple calculus to show that the gradient is going to be follow this expression. And notably, this is by chain rule proportional to the gradient of the loss with respect to the output. Okay, so what is this? This is basically nothing but the difference between our current prediction and the true labels that we get from the trained data. Okay, so what this means is that, as we talked about before, the worse our prediction, the larger the gradient. Therefore, the larger the updates, and hopefully the faster we can converge to a good predictor. Okay. It turns out that a similar thing also is satisfied for the classification problem, in particular the softmax classification problem, when we use the cross entropy loss. Okay. So this was our prediction. Okay. Which basically is nothing but applying the softmax normalization to this linear model. And again, notice that without loss of generality, I'm ignoring the bias term. So for training, again, we use SGD to minimize the empirical risk minimization problem with cross entropy loss. Again, by chain rule, the gradient that we're going to use to update the parameter is going to be sort of proportional to the gradient of the loss with respect to the output. Okay. And it is a very simple calculation that I'm ignoring here to show that the gradient of the loss with respect to output is again going to be exactly the difference between our prediction and the true labels. Therefore, in both cases, the larger the error or our residual, the larger the gradient or this useful signal that we are leveraging to update the parameters of our model. So basically, we talked about simple regression, linear regression, and linear classification problems. In the next lecture, we're going to talk about the need to go beyond these simple models. I'll see you there.